the reminder. Okay. So power device. Okay. So in the previous or our first meeting, so we have introduced you about what is actually the power electronics is all about. And for this course, for this class, so we will introduce you about the power device, which is the main component inside the power electronic circuits. Okay. So I'm using two screen right now. Okay. Okay. So as mentioned before, uh, in power electronics, okay, so the device that we use is actually what we call the semiconductor, okay, semiconductor device. So semiconductor device, it can be a diode, it can be the thyristor or SCR, and it can be transistors. So this is the three main electronic component that make up the important part inside the power electronic circuit. Okay. And also previously stated that for power electronics, this device is, okay, sorry, this device is used as a switch, okay, as a switch, meaning that it is on and off, okay. So meaning that it is switched on and off, so it will have frequency. Okay, so because of on and off, regular cyclic on and off, so it is has some frequency. So for the to select a suitable power device, whether to use diode, SCR, or transistors, these are the two main features that you need to consider before selecting which is the suitable device for that particular application or that particular circuits. Okay, the first is the switching speed. Okay, so some device has limitation in terms of the switching speed. It cannot switch at very high switching frequency. So the switching frequency for this power electronics, it can be from 1 hertz to 100 megahertz. Okay, so the switching frequency that we talk about is actually from 1 hertz until the maximum maybe 100 or maybe 1000 megahertz. Okay, that is the switching speed. Okay, this is the first features that you need to consider. The second features that you need to consider before selecting uh, the suitable power device is the capability of that device to handle high power, low power, or medium power. Okay, so this power is actually depend on the voltage and also the current. Okay, so some of the device, it cannot handle high voltage, high current. So that device should be used for low voltage and low current. Okay, so I hope you understand. So this is the two main features that you need to consider when selecting a suitable power semiconductor in your circuit. Okay, so as you can see, this is the graph that power versus frequency. Okay, so this is actually the limitation. This curve is actually the limitation for the real switch, okay, that available in the market. So as you can see here, so there is no such device that can actually handle both, meaning that at this position. Let me erase this one. Okay, there is no such device that can handle at this position high power and high frequency. Okay, there is no such device in the market right now that has capability of high power and high frequency. The only actually the device that available in the market, whether the device is capable to handle high power, high frequency, but the limitation is that it cannot handle high power. Okay, and as you can see also here, some of the device, the maximum it can actually go for high power, but very low switching frequency. So there is no such device that actually capable to fulfill these two requirements. Okay, high power and high frequency. Okay, so actually the device, for example, I just put an example. The device that is actually can handle high power but very low switching frequency is diode and also SCR. And the device that can handle, that can be switched at very high switching frequency, but the limitation is actually on the power, is actually MOSFET, transistor MOSFET. Okay, this MOSFET is able to be switched at 1 megahertz or 100 megahertz, but it cannot handle high power. So this MOSFET need to be used at a very low power application. Okay, so I hope you can understand this curve. Okay, this is actually the limitation of the real power switch. Okay, next. So what is actually a switching circuit? Okay, so the concept of the switching circuit can be uh, depicted or illustrated by using this very simple circuit. For example, we have the voltage source here. This is an AC source, okay, which is, you can draw like this, which is a cyclic. You have half cycle, and then T is at the full cycle here, okay. And we have a resistor as a load, and this terminal, these two terminal is an open circuit terminal just for measurement purpose. So this one maybe you can just put an oscilloscope, okay, oscilloscope to see what is the waveform at the output side, okay. And this is the power electronic device, okay. It can be either diode, it can be SCR, or it can be transistor. And this is actually the control signal, okay, on or off, given to the power device, okay. So this signal is generated from the microcontroller. Okay, so for example, for this circuit, you force or you give a signal to give the switch to turn on from 0 to half cycle, from 0 to half cycle. So this switch is on. Okay, so you give control signal to turn on this switch from 0 to half cycle, and uh, from half cycle to full cycle, you give the signal to the switch to turn off. Okay, so a very simple circuit here. So from here you can see that when you turn on this switch, okay, what will happen is that you will see that V out is connected with V in. Okay, so meaning that your V out is V in from this time period. So your voltage output waveform will be have a same waveform as your V in from 0 to half cycle. Okay, and when for the half cycle to the full cycle, the switch is off. Okay, so the switch is off. So when the switch is off, your V out is no longer connected to the source. So your V out is 0. Okay, because there is no connection. So meaning that the full waveform for your V out is like this, from 0 to half cycle, and then from half cycle to full cycle is 0 voltage. Okay, and then it is repeated again and again. Okay, so you will have a waveform V out is like this. Okay, 0 to half cycle and so on. Okay, so this is actually a very simple circuit, which is actually this one is what we call because this is AC signal, AC input, and then this is your V out. So this is actually, as you can see, this is what you call a rectifier circuit. I think you have met this rectifier circuit during your electronic course. Okay, during your electronic course. A very simple rectifier circuit, where the implementation of the rectifier circuit in real application is by using a diode. Okay. So for the diode here, as you can see, there is no signal input. Okay, there is no signal control here. So the diode is turned on because of the forward bias. So I hope you can recall that for the diode, to turn on the diode, what we need to do is, this is anode and this is cathode. So the anode must positive compared to cathode. Okay, so this diode will turn on. So when this diode is turned on, so V out is connected to V in. So that's why you have this waveform. Okay, and when the polarity is okay, so this is first for this one. And when the voltage source is changed, the polarity, meaning that this polarity is changed negative to positive here. So this meaning that this one cathode is positive compared to anode. So the diode is reverse bias. So meaning that it is disconnected. Okay. So V out is disconnected to V in. So that's why you have zero voltage. So that is the concept of switching circuit. Okay. Okay. Switching characteristic. Okay. So from on to off and off to on. So there is some characteristic that we need to study. Okay. So for switching characteristic, we need to study the first one is what we call the ideal switch. What is ideal switch? And the second one is actually called a real switch. So it actually depends on, so either switch and real switch is actually depends on how you want to do the analysis. If you want just to analyze whether the circuit is on, is can run or is can run properly, simulate, run, then it's okay to use idle switch. But if you want to do the analysis more towards on the losses, more towards on the efficiency, so your simulation file or your simulation model should include the real switch characteristic. Okay, so let's go what we call, what is actually definition of the ideal switch. Okay, so the ideal switch, we consider the switch has no power limit, meaning that the transistor, the diode, and the SCR has limitless power. Okay, so unlimited voltage and unlimited forward current. So I will explain what is voltage block and what is the forward current after this. Okay, no power limit. The second characteristic of the ideal switch is that there is no delay in terms of turn on and turn off. Okay, so zero turn on and zero turn off. And the frequency value switching is also unlimited. It can switch at 1 gigahertz, 100 gigahertz. Okay, so there is no limit because this is ideal. We didn't consider limitations. Okay, so it can be switched up to 100 giga. So this is what I did is switch only available during the simulation lah. So during the hardware, so this idle switch is not valid. This is idle switch. That is why I say that for idle switch is depend on how you want to do the analysis. What analysis that you want to do. If you just want to see the circuit is running properly, then it's okay to use idle switch model. But if you want to use to analyze the losses, okay, the efficiency and so on. So it's better to use the real switch characteristic. And the third one is that there is no power dissipation. So meaning that we ignore the internal resistance that may exist inside the switch. Okay. So this is actually the waveform that shows about the characteristic of the either switch. So this is the, for example, this is the switch, and you can see that we have current flow, and you have a voltage across this switch. Okay, so I think I need to draw one more waveform here. Okay, so this is the signal switch. Okay, signal switch that come from signal that come from your microprocessor. Okay. So this is on, meaning that this is off. This is the signal off, and then this is the signal on. So that you can see the relationship. Okay. And I would like also to draw again this very simple circuit. For example, this one is 100 volt, for example, 100 volt DC. And then you have a switch here, and then you have a load. Okay. And then this signal is controlled by your microprocessor. Okay, so the signal comes from the microprocessor. On and off is controlled by this signal switch. Okay, so let's see when the switch signal is off. Okay, when the signal comes from the microprocessor give an order for this switch to turn off. Okay, so this is signal off. So what happened when the switch is off? So when the switch is off, okay, so meaning that, okay, off. Okay, so when the signal is off, can you calculate for me what is the voltage across the switch? This is the positive, negative. This is your voltage across the switch. Okay, so for example, this one may be 10 ohm. Can somebody calculate for me what is the voltage across the switch when the switch is off? Okay. This is the signal switch come from the microprocessor. So it gives the order for the switch to turn off. So right now the switch is off. Okay, so this is actually the voltage waveform across the switch. Okay, so right now, as you can see, when this switch is off, you will have a voltage across the switch, right? And since it is off, the current is also zero, right? So that's why you have zero current here. But there is a voltage across the switch. Can somebody calculate what is the voltage across the switch? Sorry, I cannot see the... Yeah, 100 volt. Yeah. Sometimes because...
Okay, isn't it short circuit because it's switch is off?
Okay, so when the switch is off, what you mean by short circuit? Because right now, the switch is off.
Open circuit.
Yeah, this is open circuit, right? So the
Yeah.
current cannot flow. So that's why you have zero current here. But there is a voltage. Yeah, this is actually the voltage across the switch. Okay, not voltage across the load. This is the voltage across the switch. And the voltage across the switch, yes, one of your, okay, so this is 100 volt, right? This is during off. So this is the characteristic during off. So during off, there is a voltage across the switch, and the current that flow inside the switch is zero lah, because there is no current, right? Because this is off. And what is the power? What is the power dissipated by this switch? Because we know this is a power is V multiplied with current, right?
0.
Yeah. Right now the voltage is 100. Okay, the voltage across the switch is 100, but the current is 0. So that's why 0 watt. Okay. So that is what we refer to. So no power dissipation. Okay. So the characteristic of the ideal switch, there is no power dissipation. Okay. Okay, and then let's look when the switch is on, when the signal from the microprocessor give an order for the switch to turn on. So when the switch is on, what happened to the circuit? Okay. So when the switch is on, so right now it's connected, right? So there will be a current flow, right? So that's why you have current. Before this, the current is 0, right? Because off. But right now, since the switch is on, so there will be a current. Okay, but you will see that the voltage across the switch is 0, right? So that's why you have 0 voltage. And what about the power dissipation? V multiplied with I when during the turn on. Same. The voltage is 0 and the current is maybe 100 over 10, right? Maybe 10 amperes, for example. But still, the power dissipated or the power absorbed by this switch is still 0, right? So that's why we say that for either switch, whether it is on or whether it is off, the total power absorbed by the switch is 0. Okay? And the second characteristic, 0 turn on and 0 turn off, is actually meaning that here, there is no transition, there is no delay. So when you give the signal to turn on, it immediately turn on, and when it is turned off, it immediately turn off. So there is no delay. So this is the three characteristic, the main three characteristic that you need to remember about the idle switch. No power limit, no delay in terms of the turning on and turning off, and the last one, no power dissipation. Okay, so that is for the idle switch. And this you can use this idle switch during your simulation file if the analysis is more towards on to see whether the circuit is operated or not. Okay, but if your analysis is more towards on to see the voltage drop, to see the power losses and so on, then you need um, to use the real switch characteristic. So this is either switch. So the next is switching characteristic for the practical or what you call the real switch. So actually, there are three main points here for the practical switch, which is actually a contradict or what I call opposite of the idle switch. Okay, so the first one for the practical switch, it depends because practical switch is actually is actually constructed based on the semiconductor materials and so on. Okay, so depending on the material used, so it has some limited power handling capabilities, meaning that it has a maximum voltage and maximum current that can flow inside the transistors, inside the diode, and so on. Okay, so for example, the voltage between across the capacitor, sorry, the collector and emitter is 600 volts. So this is the rated or rated voltage, okay, that is allowed to be used, okay, for this transistor. For example, if the vces is more than that, so your transistor may become very hot and it will break down. Okay. And the second one is the delayed turning on and delayed turning off. And the third one, it has some power dissipation because of the internal resistance inside this device. Okay, so this is actually usually the parameters that you will actually see from the database. Okay, for example, this one is G4PC50U. This is a transistor N channel. Okay, this is the N channel. So it has this one. So what is actually this one? What is the VCES 600 volt? What is the VCE on 1.65? And what is IC 27 ampere and so on? So this one will be, I will explain later. Okay. So I hope this one you can actually have currently know what is the difference between the ideal and practical switch. So this is actually the waveform that actually want to show the characteristic of the practical switch. As you can see here, okay. So this is actually same. The signal switch is actually same. So this one is off signals and this one is on signal. So this is off. So this is a signal, okay, signal from the microprocessor, and this is on and this is off. Okay, so you will see that I think this one is start here on. Okay, so you will see that even though you give signal on, it didn't turn on. It didn't turn on immediately as in the ideal switch. Okay, it has some delay. So it will slowly rise up and so on. The same case goes to the voltage. Okay, the voltage will reduce. So actually, as you can see, there's a delay to turn on immediately. Okay, so that is what we talk about this one: delay turning on and delay turning off. Okay, it requires some time to fully on. Okay, so fully on, the current is actually rising when the voltage across the switch is off, is zero, decreasing to zero. Okay. Okay, and then you will see that during on, this is on. Okay, there is some voltage drop. There is some voltage drop. For the ideal switch, during on, the voltage is zero, right? But for the practical switch, there is some voltage drop due to the internal resistance of the device. Okay, so as you can see, the power, which is V multiplied with the current. So during turn on, there is a voltage here, very small voltage here, and a very large current because right now it's turned on. So there will be some power. This is the power. Power dissipate, power absorbed by the device. Okay, so during turn on, and as you can see also during the transition from off to on, okay, so you have the voltage and you have this current. So the overlapping of the voltage and current will also give you power losses during the switching. Okay, so during the switching also we have losses. During on also we have losses. And during off, so what happened when during off? So when during off, the current, even though the current should be 0, but there is some leakage current inside the real switch. So we have a very small current, and this is the voltage across the switch. Okay, so very high voltage here because it is off. So as you can see, V multiplied with I, so we have the power losses also. So meaning that during off, during the transition of the switching, and during on, we have power losses. Okay, power absorbed by the switch. Okay, so this is the characteristic of the real switch, okay, or practical switch. And it is very contradict with the idle switch. Okay, so just to clarify, the idle switch is actually is not real. Okay, it's not available in the market. Idle switch is more towards on the simulation purpose, just to study whether the circuit is operated, function or fully function or not. Okay, but in the market you cannot get that ideal characteristic. Okay, because every materials, every semiconductor, they have some internal resistance. So due to that internal resistance, it must have some voltage drop during switch during the on state. Okay, so that's why every state during off or on or during the transition, you have losses. Okay, so this is actually the idle switch and practical switch summarized. Okay, the summary of that. Okay. Okay, I just want to explain a little bit about what is this actually. What is the VCES? What is the VC on? And what is other this one? Okay. When you actually go for to find out what is the suitable device, usually the transistor or diode, okay, you need to look at these three parameters. What is the VCES and so on. So this is actually is the voltage rating. Okay, voltage rating. This one is the current rating. And this is the, because it is on right now. VC is on. So meaning that this is the voltage drop during on state. Okay, so this one is actually this one. This is the V on, which is the voltage drop when your device is in on state because of some internal resistance. So it varies very small, 1.65 volts. Okay, so this is the voltage drop across the switch when it is at on state. Okay, and what is this? What is the VCES 600 volt? So this is the voltage rating during off state. Okay, you see that during off state like this. Okay, during off state. Okay, during off state. So this is the value. For example, for this application, during the off state, the voltage, the value of the voltage that required by the switch to block is equals to 100 volts. Meaning that if you put these transistors with the rating of 600 volt, then it's okay because because the rating is 600 volt, so it's lower than the rating. Okay, so 100 volt is lower than 600, so it's okay. But if the voltage here is 1000 volts, and then you use this transistor with a rating of 600 volt, so your transistor will break down. Okay, because these values is actually referring to the what is the voltage value that it need to block during off state. Okay, during off state, what is the voltage that it need to block? For example, for this one, based on the KVL here, the maximum voltage that the switch need to block is 1 kilovolt. So you need to find a transistor that has the voltage rating higher than 1000 volts. Okay, so I hope you understand. This one is the voltage during off state. What is the value of the voltage that the switch need to block during off state? And this one, when you see something like on and so on, so this one is the this one is the voltage drop when the switch is on. And the current here is usually the current what is the maximum current that can flow inside the device when the device is on. Okay, because they have least limitation because of the material use. So some materials capable to handle high current, but some material cannot handle high current. Okay. It's like I can give a very simple examples lah. Like we have you have a cable, right? A wire, a cable here. For example, I show this one. You have a cable. So this one is very not very thick. Okay. So I don't know. So actually, the size of the cable will determine what is the maximum current that can flow. So if I use this cable, okay, I use this cable, and then the current that will flow inside this one is 1 kilo ampere. So this cable cannot handle that because the material used, the core here that use the copper is not very thick enough to handle that high current. So my cable will burn out very quickly. Okay. If I want to use 1 kilo ampere current, I need to use maybe a larger cable. Okay. So this is what I want to give you example. The difference between the practical implementation, practical switch, and the ideal switch. Okay, for the ideal, meaning that for simulation, you don't care whether your cable is good enough to handle that high current or not, right? But in the real application, there are a lot of consideration that you need to consider. Okay, for
Doctor,
example, yeah,
usually the question is based on ideal or practical.
it depends on the questions. Yeah, depends on the question because you mean for the test and final exam, is it?
Yes.
Yeah, it depends on the questions. So some questions use ideal switch, some question give you some values, for example, like this, and then calculate the drop, the voltage drop, the power losses, and so on.
Okay.
Okay. Okay. So I hope you understand on that. Oh, dah 12.26 eh. Okay, I think okay, so just a brief introduction about the power device categories. So actually, as stated before, we have three components, the three main devices in power electronic, which is the diode, and then we have the SCR, and then we have the transistors. Okay, so actually the diode is actually we have two types of diode. The diode that used for the electronic circuit and the diode used for the power circuit. So to differentiate that, we sometimes just write down as a power diode. This one also power thyristor and power transistors. Just to differentiate between the transistor that's suitable for electronic circuit and the transistor that's suitable for power circuit. Okay, the different electronics, because the voltage is around 5 volt, right? The current is milliamperes and so on. But power circuit is up to 1 kilovolt. The current can be up to 1 kiloamperes. So that is a difference. So meaning that the rating for the power diode is actually not similar with the rating of the electronic diode. Okay. So we categorize this device into three. The uncontrolled, meaning that we cannot control the diode. Okay. We cannot control the diode. It depends on the forward bias or reverse bias of the circuit. The second one, we can control, semi-control. We can control on states only. But to off, we cannot control. And the last one, which is the most powerful device, is actually transistors. Fully control meaning that we can control when this device need to turn on and when to turn off. So we have this one, MOSFET, IGBT, GTO, IGCT, and also BJT. Okay. So I think that's all from me today. So we will meet again next week on, we will introduce you each of the device, for example, the diode, okay? So the symbols and the models that are available in the market and so on, okay? So that's why I emphasize more on the voltage blocking, voltage drop, current, forward current, and so on, because it's related to this one, okay? So rated maximum voltage, what is the rated maximum voltage? What is the rated current and so on? What is the VF here? VF is actually a voltage drop. So that's why I emphasize more on that today, okay? Because we will deal with this later next week, more on this, okay? So I think that's all from me. Thank you very much for your attention. Sorry for the attendance because the portal is broken, okay? It's offline. So any question that you want to ask before we dismiss?
Yes, doctor.
Yeah.
Yes, doctor. Do you have a specific reference book, or like, do you advise us to take a specific book for this subject?
Yes, I have already explained it in
Yeah, in the course. Yeah, but there's many, not one.
yeah,
So
the first one, the textbook, Daniel W. Hart.
the first one. Okay, thank you.
Yeah, Daniel W. Hart. That one is very fundamental. That one is very good for the undergraduates. You can refer that. Okay. Okay, I think that's all from me. Thank you very much. Any other questions from the chat? Sometimes because I cannot. Okay. Okay, thank you very much. Okay, assalamualaikum.
Thank you, Doctor.
Yeah, and have a very
Thank
good
you,
day.
Doctor.
Okay.
Thank you, Doctor.
Thank you, Doctor.